So let us discuss an example of Bayesian method when my parameter is a continuous random variable, and we will use Excel sheet to plot the prior distribution, maximum likelihood function and posterior distribution in this case. So let us consider design of tall buildings. So for designing a tall building, one important load, that is wind load. So basically, whenever we are designing a tall building, we have to consider two things. One is what is the maximum annual wind speed. So that is called maximum annual wind speed. So this means what is the maximum wind speed in a given year that has been observed. So basically what we are doing is every day we are taking the reading for wind speed and we are plotting, and then we are looking at what day is the maximum wind speed and corresponding what is the value. So that is our maximum annual wind speed. Another parameter, that is design wind speed. So whenever we design a building, we have to see that my design wind speed should be not exceeded frequently by the maximum annual wind speed. So my target is design wind speed should not exceed, so design wind speed should be greater than maximum annual wind speed. So this is maximum annual wind speed. So this is the ideal case, but if I follow this, my building will be very costly. So this is uneconomical. So in that case, what we can do is we can say, okay, few times it can exceed the maximum annual wind speed. The probability of exceedance should be very low. So that's why these two things, that is design wind speed and maximum annual wind speed, is important to calculate the probability of failure of such kind of buildings or probability of exceedance of maximum annual wind speed corresponding to the design wind speed. But the problem is, when we are going to design a building in a new area, we don't have the data. So there is a lack of data in this case. For example, if I want to design a building in certain city that is relatively new and we don't have the design wind speed data or annual wind speed data, then how we can come across the design wind speed? So lack of data is often a case. So what we do in those situations, what we do is we take another city and corresponding to that we know the design wind speed. So we take all this data, we plot a histogram, we fit a distribution, and based upon this fitted distribution we find the parameters. And those data is used as a prior for this city. So what I am saying, so let's say this is for city 2, we have the observed wind speed data. So we'll use the data that is coming from city 2 to define a prior distribution for city 1, that is relatively a new city, where we don't have the long-term wind speed data. So let's say 100 years of wind speed data. But for city 2, we have hundreds year of wind data. So we can plot this data in a histogram, we can fit a distribution, and we can find corresponding mean of the distribution, a standard deviation of the distribution, and corresponding coefficient of variation of the parameter. And we'll use this to define my prior for other cities. So let's use all this idea through an example. So this example says an engineer is designing a temporary structure subjected to wind load on a newly developed island of interest. So this is a newly developed island, so of course we will not have much of the wind speed data. So of interest is the probability P that annual maximum wind speed will not be exceeded by 120 km per hour. So in this case 120 km per hour is my design wind speed. So this P is the probability that annual maximum wind speed will not exceed corresponding to the design wind speed. Record for the annual maximum wind speed in this island is available only for the last 5 years. So we have very small data, and among these 120 km per hour wind speed was exceeded only once. So based upon this, what we can say? We can say there is a 1 by 5, that is 20% probability that wind speed or maximum annual wind speed will exceed the design wind speed. So this is, so we can say in this case there is a 20% probability, that is P is equals to 0.2. But now we can also use, if I have a long data for other cities, then we can find distribution for P. So let's say we have another island in this region that has a longer record of wind speeds. However, it is at some distance away. Of course, this is not the exactly same situation. So this is at a distance away. So we can use that data and we can only represent, we cannot have exact wind speed for this city. So after a comparative study of the geographical conditions in two islands, the engineer inferred that longer record that average value for P for newly developed island is 2/3 with coefficient of variation is 27%. So what we are saying, for this city that is relatively far away from the newly constructed city or building, this has a long-term data, and now if we plot this data in a histogram, and then if I fit a distribution, corresponding mean is that is probability is 2/3 and coefficient of variation is 27%. So now we can use this idea to fit a distribution. So let's say since P is bounded between 0 and 1, the following beta distribution can be assumed as a prior distribution for the wind speed for newly constructed buildings. So this is the prior distribution. So let's say now we know the prior distribution, and this prior distribution has come from another city that is far away from the newly constructed building. So now the question is, what is the likelihood that annual maximum wind speed will exceed 120 km per hour in 1 out of 5 years? So that is, we have to find the likelihood function. So first let's find prior. What is prior in this case? That is f dash p, that is given 20 pq 1 minus p, where p lies between 0 to 1. So this is given. Now likelihood function that says 1 out of 5 years, it will exceed 1 out of 5 years. This means out of 5 years, 4 years will not exceed. So 4 years will not exceed out of 5 years. So I am writing in terms of will not exceed. Why? Because P is the probability of will not exceedance. So if you see the problem, so what is this P? So P is the annual maximum wind speed will not exceed the design wind speed, that is 120 km per hour in this case. So now we can use binomial theorem to find the likelihood. So this will be 5c4, that is 4 year out of 5 year will not exceed, and in 1 year it will exceed. So this is the corresponding likelihood function. So this is likelihood 5c4 p raised to the power 4 1 minus p raised to the power 1. So now let us estimate the posterior probability for p. So we can find posterior distribution. So if you remember posterior distribution f double dash p, this is nothing but k times likelihood function times prior. That is k times L times f double dash p. And this likelihood is also function of p. So we can write this here. So k times likelihood function is 5c4 p raised to the power 4 times 1 minus p, and prior is given, that is binomially distributed 20pq1 minus p. So this function where p lies between 0 to 1. So this is 20pq 1 minus p. So we can further write k times 5c4 p7 and 1 minus p whole square times 20. So this becomes 100 times k p7 1 minus p square. So this is my posterior distribution. So k is normalization constant, and that is simply 1 divided by integration of 100 p7 1 minus p square dp, and p lies between 0 to 1. So if you perform this integration will come 3.6. So if I plug this value, I can write posterior distribution again 100 times 3.6 into p raised to the power 7 1 minus p whole square. So this is 360 p7 1 minus p whole square. So this is posterior distribution. Now we have prior distribution, likelihood function, and posterior distribution. So this is posterior distribution we just calculated, and we also have the likelihood function, and we also have the prior distribution. So now we can use Excel sheet to plot the prior, posterior, and maximum likelihood function. So let us use Excel sheet. So in this Excel sheet, on x-axis p is the prior. So let's first take p, and we have increased with 0.05. So first is 0, then 0.05, 1, 0.15. So these are the possible values of p, and this lies from 0 to 1. Now for the prior distribution, this function we have, that is 20pq. So this function here, so this is 20pq 1 minus p. So let's calculate prior distribution first. So this is equals to 20 times p is this raised to the power 3 multiplied by 1 minus p, and p is nothing but a2. So this is 20pq1 minus p. So 20 times a2 raised to the power 3 times 1 minus p2. So this is the prior value. So if I double click, I will get all this prior distribution, and this prior distribution is plotted in this case. So this is the prior distribution, and then the same prior distribution p versus, so we have a graph for p versus the prior distribution. Let's calculate likelihood, and then we will discuss more about this graph. So this likelihood function, this is equals to 5c4 p raised to the power 4 into 1 minus p. So this is 5c4 is simply 5. So I can write this as 5 times p raised to the power 4, or I can use binomial distribution function. So this is equals to binomial distribution. So Excel has a binomial distribution, then I have to put tab key. So numbers and trials, so we have 4 numbers of success and then we have 5 trials, and the corresponding probability is this, and then we need a basically not a cumulative, so let's put false, and this will give me the likelihood function. So if I double click, this is the likelihood function, and this is shown here with the red line. Now we can plot posterior distribution, that is 360 times. So this is equals to 360 times p raised to the power 7. So this value raised to the power 7 times 1 minus p, and this p is this value. Now, so there are some, so 360 a2 1 minus a2, so I put double 2 times equal to sign. So this is equals to 360 into a to the power 7 into 1 minus a2. Now this gives me the posterior distribution. Basically we have 1 minus p square. So let's revise this formula. So this is my posterior distribution. Now we have plotted here the prior distribution, posterior distribution, and the likelihood function. So this is my so you can double click here and see which data is this. So this is posterior distribution. So this is posterior, and this data, this is prior. So this, the blue one is prior, and this red one is likelihood function. So you see, my posterior distribution is sharper than prior distribution as well as likelihood function. So this is because we are incorporating the data into the analysis, and that's why posterior distribution becoming sharp. So let's come to the slide. So basically the posterior distribution is sharper than either the prior distribution or the likelihood function. So this implies that more information is contained in the posterior distribution than either in the prior distribution or in the likelihood function. So this illustrates how we can use Excel sheet to plot the prior, posterior, and likelihood function, and how we can use Bayes theorem when we have continuous case and the data is not available for a particular site. Then we can use the prior distribution that is coming from other side or the domain knowledge, and this prior can be integrated with the data. So we can stop here and we'll discuss next in another example in the next lecture.